Okay, so thank you. Hope you hear me. So I present some very basic things about domain decomposition. So stay with me. I try to keep things as basic as possible. But keep in mind, even if you're doing more complicated things, you'll meet the same kind of objects that I'm presenting you here. So I put here some collaborators because we wrote a book with Frédéric Nataf and Pierre Jolivet. So what I'm presenting here follows a bit the lines of the introductory part of the book. You can download this book for free on my webpage and also the programs, and you can use them freely. And Pierre-Henri was a postdoc with Frédéric Nataf, and he worked a lot on the software part of the domain decomposition. So that's why I wanted to acknowledge his contribution. Okay, so I won't present everything here, but I'm just starting. My aim is to present you the first part. So it's just to do an introduction to domain decomposition methods. Right, so I start with a few images which are a bit outdated. They are probably 10 years ago from the research point of view, but I became very affectionate to these two because they are related to my own research. They reflect some difficulties that you might encounter when you solve PDEs. And for example, this one, which is a real difficulty still right now, if you want to solve partial differential equations which are indefinite and in high frequencies and in heterogeneous media, because the head is a heterogeneous media, they are still very, very difficult to solve as for 2020. And here on the right-hand side, you have, here I just wrote the PD, which is linear elasticity, but the tire here, it's typically a multi-scale nonlinear structure, so you have to solve something which is very complicated, heterogeneous, nonlinear, and large scale, right? So if you suppose that you want to discretize this, you end up with a very large linear system. And the matrix will inherit all the bad properties of the PDEs. So here the bad properties are non-self-adjoint, for example. And also this is very large and ill-conditioned, but it's the nice quality is that it's sparse. So this is pretty much the only thing. Right, so now you want to solve it, so you probably learn from third-year lectures. You have direct solvers, and here you have a lot of different libraries that allow you to solve direct solvers in a very efficient way. And you have also iterative methods, very basic one, like fixed point iterations or Krylov type methods, right? Like conjugate gradient, GMRS, and so on, right? So here just something to illustrate what are the qualities and the downsides, the advantages and downsides of each one. So for the direct methods, the downside is that they are very is the memory consumption. However, they are very, very robust. So here it's gray, parallelizable, because in the latest year people improved a lot this parallel aspect of direct methods. However, it's not green, it's not ideal, right? At the same time, iterative methods, they are very good from the memory point of view. They are based on matrix vector multiplications. So they're very parallelizable, but they are not robust because the convergence depends on the matrix, right? So why do domain decomposition? Because obviously it's the best of the two worlds. So they take all the greens of here, memory consumption, parallelizable, and also the robustness, right? So here it's I also keep this table because it's very nice and allows you to understand the complexity issues. So suppose we are in the framework of sparse linear algebra. So we solve PDEs, we discretize, we get up sparse linear matrices. And what is the complexity if you want to solve a linear system A U equal to B? So if you take, for example, the Gauss method and you consider your matrix as dense, you learn in the third year lecture that the complexity over order of n cubed, which is really bad. But if you use, the band structure as sparsity, you can reduce a lot the complexity when solving a linear system, okay? So that means as of today, which is a bit outdated again, with your laptop you should be able to solve something that it's at least 1 million unknowns in 2 dimensions or 100,000 in 3 dimensions, yeah, linear system. So again, you have a lot of sparse direct solvers, a lot of libraries. You have MUMS, this is French, right? You have UMFPAC. If you use MATLAB and use the / command, this is the UMFPAC which is behind it. Okay, so now a lot of few pictures that I also like again. So so then if you want to solve a linear system and you have a large matrix, you just buy a supercomputer if you have money, or just a very good one, or you wait a few more years to have a nice, better computer, right? So this is also known as a Moore law. So that means every 18 months the number of transistors in a computer doubled, right? And this is also very, paired. Usually with nanoscale, the power density stays constant. But the problem is that as of 2005, this Moore law broke. So the clock speed of the transistor stalled at 3 gigahertz, right? So that means most of the constructors, they decided just to put more cores in a supercomputer instead of just hoping having something faster. So that means the most of the supercomputers here, it's again, stops at 2019 here. So the number of processors is now at 100 million and even beyond. And also, if you look here, the number of floating point operation per second, we are roughly in the exascale era right now entering. So you can perform with these supercomputers 10 to the power 18 floating point operation per second, right? So this is really huge. So now you said, okay, then I don't have a parallel computer, and I would contradict. I said, of course you have, because your laptop has a lot of cores already. So my own laptop that it's bought on 2021 has 10 cores. So you can already do the parallel computing on your own laptop, right? Not to mention the desktop computers, the clusters, and also the supercomputers with a lot of cores, right? So, I mean, anyone can do now a parallel computing. Also, you might say, okay, I have CPUs, but now the GPUs are very fashionable. So the question is, GPUs are not the fastest. They are newer, processors. These are ARM processors, which are far faster than the GPUs, right? And so the information, okay, here change a bit, because Fugaku is no longer the top 500. The first is the second run, right? But anyway, the second supercomputer in the world has this ARM processor, right? And moreover, which is very attractive also with respect to the GPUs have this proprietary software like CUDA and so on. So all these ARM are programmable with the standard low-level languages that are open. Okay, so Fortran, OpenMP, MPI, right? So now you say, okay, I'm not an expert in parallel computer, even if I have a lot of cores, yeah, and I could do, but I'm not an expert. So what should I do? I'm not able to program everything. So the good news is that you don't need to be an expert in parallel computing to use this, because there is a software. So in the same time with the hardware, software developed very easily. So the parallelism is already embedded in high-level languages. So it means you just take this high-level language and you use it, and everything is hidden, the parallelism inside, right? So now just to give a few examples. So for example, if you work on finite element, finite volumes, there are a lot of open source, high-level, like OpenFOAM, FreeFEM, FireDrake, Dune, just to name a few. And my collaborator Pierre, he's the origin of this HPDDM and so on. And there are more, famous PETSI and Scalapag and so on, right? So that means there is a software and hardware, so you can do parallel computing very easily, even if you're not an expert and if you want to solve a large-scale problem. Right, so now let's go back after this introduction, which is not that short, but I think it's important because I just wanted to make you aware that if you want to solve a discretized linear system, you can solve it in parallel by using, and you have everything available, right? So now what kind of methods do you use? So here I try to introduce you very, very slowly and gently to domain decomposition methods by using very basic notions. So let me start by the original Schwarz method. So this is a method was initially introduced by Schwartz in 1870 to prove existence and uniqueness of the solution of this problem in a generally shaped domain. So it was not meant for parallel computing. So how does it look like? So the Schwartz method, you want to solve this problem, and you find an iterative method, and you start from initial guess, and then you compute the n+1 guess in the domain 1 and the domain 2 from the n guess by solving one boundary value problem in the left domain, one boundary value problem in the right domain, and then you exchange, you take iterate the data from the other domain at these interfaces, the artificial boundary, they're called interfaces, right? So this is an alternative method, alternate method, because you solve first here, then you get the solution, you give the solution to the second domain, which will solve, and you give it back, and so on. So this is an alternate method, right? But obviously in the 90s, 70s, 80s, so this regained a lot of interest, because you see, if you just forget about the alternate aspect here and you just remove this +1 here, this will come fully parallel. So that means you solve a Laplace problem in the first domain, solve a Laplace problem in the second domain, complete in parallel, they exchange the data only on these interfaces, and this will get you the first parallel algorithm, right? Which starts from the historical original Schwarz method, right? Okay, so what are the problems here? So I just put here a few things. So the parallel algorithm, as I define it here, converges but very, very slowly. And there is something here, so you need, in order to make it converge, you need an overlapping here, overlapping the so these two domains need to overlap, right? And we also wanted to give it a name, even if it's probably not a well-established name in the domain decomposition community, but we want to call it Jacobi-Schwarz method. I will explain a bit later why, right? So this is the simplest domain decomposition method. It's purely iterative, has been introduced with a different purpose than the parallelism, solving the parallel solve of PDEs, right? But it ended up as a parallel solution of PDEs. Okay, so now let's try to formalize a bit better this. So this is the initial Schwarz method. So now we want to put some formalism. I wanted to show you that in fact this Schwarz method is nothing else but a Jacobi method in disguise, right? Under certain condition, right? So that's why I call it Jacobi-Schwarz. So let's start. So first of all, the algorithm acts on local functions. So if you look here, local functions, so that means U1 and U2 are the restriction of the global solution to the local domains. So that's why we call it local functions, right? I would like something that will be, global. So I just want to write something globally, right? So for this, I define extension operators. That means for any function which is defined on the local domain. So the extension operator is just the extension by 0 outside the local domain. So here, don't expect a lot of mathematical rigor. I just want to show you things in a simple way, right? So you don't get lost. So what else do I need? So here, these are very, very important objects that you will meet also in more sophisticated methods. The second object is partition of unity functions. So partition of unity, as the name shows, so they are local, they are defined as local domains, they are positive, they are 0 on the boundary, and these partition of unity functions applied to a local function, and then if you extend, the sum will be simply the global function, which is a very simple idea. Here I just put two domains, not to confuse you, but it's a very, so you can imagine if the domains do overlap, then partition of unity is simply something that can be 1, 0, 1/2, 1/3, right? And if you want something to be smooth, you have something that decreases smoothly from 1 to 0 in some way in the overlap. Okay, so now let me denote by UN the approximation of to the solution of the global Poisson problem, right? So this is a global approximation, and UN+1, it's computed by solving local subproblems and gluing them together. So now I'll try to express this whole process by using the object that I just defined here. Okay, so I repeat again. I will repeat a lot of things here. So I have two local problems to solve, just to fix ideas, right? So UI n+1. This is the global boundary condition. This is the local boundary condition. And this is the interface, right? So the intersection of the local domain with its neighbor. Okay, so now if I want to write this process in a global manner by using the object that I just defined, it looks like this. I just have, my local solutions, of these local problems. I apply the partition of unity to them, the extension operator, I sum them up, and I get the next iterate at the global level, right? So this is a this summarizes what happens here in my algorithm. So now again I will introduce two elements of vocabulary. So here you see that I have used the word restricted. So additive Schwartz, I will explain a bit later additive, you know, intuitively because I sum things up here. Restricted is because I use this partition of unity here. So if I don't use any partition of unity, you might imagine that this is not strictly true, because if you sum things up in the overlap, then you have too much information. So this is something that will not converge an iterative manner, right? But I still define it because it has an interest that you'll see a bit later. So now I have two algorithms, so restricted additive Schwartz and additive Schwartz, which means I solve locally local Dirichlet boundary value problem, I extend and I sum them up and I get my next iterate. Okay. So now, this was just the formalism, the story of the initial Schwartz algorithm, the one introduced by Schwartz, okay? Now I just move on to something else, which is not completely different, you will see later on, because then I link the two, yeah? So I go back to something that you see in the third year lectures, numeric analysis, the Jacobi algorithm, and then you'll see the link between Jacobi algorithm and the Schwartz algorithm. So, what is the Jacobi algorithm? So again, you want to solve a linear system, you have a matrix, a right-hand side, and the solution is denoted by U. So, the Jacobi algorithm, you just split, you just take the diagonal part of A, and you create here a splitting, you just keep the diagonal part of A, and you define an iterative method. So, you just compute UN plus 1 from the UN, and here you just keep the D, right? So it's very easy to see that if this algorithm converges, that will converge to the solution of this linear system, okay? So in an equivalent manner, you can write this. You can see here that this is exactly the residual of the iteration n, that you can denote by Rn, so residual vector. So that means your Jacobi algorithm can be written as UN plus 1, UN plus D minus 1, the residual vector. So now let's increase slowly the difficulty, which is not a huge difficulty, but just do things progressively. So if you want to define the block Jacobi algorithm in a similar manner, you just split the set of indices in two sets, right? And then you define U1, let's say the part of the global vector, which corresponds to the first set of indexes, and U2 the second set of indices, and you do the same for the right-hand side, right? Again, you split the linear system here, the matrix A, into blocks. Okay, so you have the blocks corresponding to U1 and U2 with a very obvious notation. So the blocks correspond to the restriction, the matrix to the set of indices. So now if you want to define the block Jacobi algorithm, you do the same thing, except that now you just take the block diagonal here. So A11 and A22 are just the diagonal blocks corresponding to A, and you have here the equivalent of block Jacobi algorithm. So now let's try to do the same thing as here. Let's try to isolate, to define some kind of residual, okay? And I get here here is the diagonal block, here is the right-hand side, and here is the matrix D, the equivalent of matrix D. And again, you can see that the block Jacobi algorithm can be written exactly as the Jacobi algorithm, except that instead of D here, this will be the block, the inverse of the diagonal blocks, right? So these are very, very simple ideas. So now what is the link with domain decomposition? So now I claim that this block Jacobi algorithm can be written in a very similar way with the same kind of objects as the objects I showed you before for the Schwartz. So that means I can use extension operator, restriction operator, partition of unity. Right, so again, now I denote by R1, R2, these are restriction matrices from the set of indices global set to the local set N1. R2, the restriction from the global set to the local set N2. And you have the equivalent, the extension operator, which are transpose operators, right? Transpose of the matrices R1 and R2. So if I use the restriction operators and the extension and so on, the block Jacobi algorithm can be written in the compact form. This is quite easy to check. I won't do the computation again. So un plus 1 is equal un plus R1 transpose A1 minus 1, R1, and the same for R2, applied to the residual vector. Okay, so now what is our A1 and A2? It's simply the restriction applied to the global matrix and multiplied by extension operators. So you can see it's a very, very nice writing, and this is something that you can generalize if you have partition in multiple blocks, not only 2 blocks, okay? So the nice feature of this that can be generalized very easily, and you'll see there is a strong link with domain decomposition. Okay, so now first part, Schwarz algorithm, second part, block Jacobi. So now I'll try to link the two. Okay, so what is the link between Schwarz and the block Jacobi algorithms? And I can show that I use exactly the same kind of formulas. But there is something that I haven't told you. I mean, there are some subtleties here. So I just choose a very simple domain decomposition in which the overlap is just minimal. I just have one mesh of overlap, right? So I'll show that in this particular case, I will stumble onto exactly the block Jacobi algorithm, as you have seen in the previous slides. Okay. So let me show you how I end up with the block Jacobi. So let's consider now, this boundary value problem, very simple one. And suppose I'm in one-dimensional case. I use finite differences, and the finite difference scheme brings me to this discretization. And here I just define a partition into 2 subdomains, and partition 2 subdomains. That means it's just you define a set of indices, the first MS indices and the next ones, and this will define the partition into domains, right? And again, if you want to solve, write it in a matrix form. You can see that the solving this and writing the Schwarz algorithm, you end up exactly with a block Jacobi algorithm. So now what is the trick? So as I said, the trick is that here I use what I call a minimum decomposition. So I simply consider 2 domains and you have a partition of indices, which apparently they don't overlap, but here you have a minimum overlap between domains, right? Just one measure of overlap. Okay, so now just to summarize, so what is the link with the extension operators that defined before? So as I said, the extension operator is defined like the transpose of the restriction operator. You hear me? Okay. So so when the overlap here is minimum, the discrete counterparts of the 3 of the Schwarz method, additive Schwarz, restricted additive Schwarz, Jacobi Schwarz, are equivalent to a block Jacobi algorithm. So now I'm just keeping an eye on time. So let's develop a bit further all these objects. So now I repeat things, but I'll try to increase a bit the difficulty in the sense that I had 2 domains before, and now I have many domains. And I try to define the restriction, partition of unity, extension when I have many subdomains. And I try to relate also the concepts defined at the continuous level to the same concept defined at discrete level. Okay, so now I have the domain, which is the union of the subdomains which are overlapping, right? I have my function u, which is the solution of the global problem. I have the restriction of u, which is simply the restriction u to the local domain. And I have the extension operator. The extension is just simply extension by 0 of the local function to the global domain. And I have my partition of unity function. So these are the objects at the continuous level. So what are corresponding objects at the discrete level? So you see, instead of just partitioning the domain, here I partition a set of degrees of freedom. So I will explain what the degree of freedom means, depending on discretization. So you have a partition of set of degrees of freedom. instead of having a function, here you have a vector of unknowns, and then you have the restriction. The corresponding of the restriction operator is simply a restriction matrix. It's a Boolean matrix, the rectangular one, and you have the extension matrix. The partition of unities are diagonal matrices with positive entries. So how do you choose them? You choose them in such a way that this equality holds, right? So restriction, partition of unit, extension, so you end up with identity, right? So this is exactly what I define at the continuous level here. Okay, so now the next part, I probably dedicate a few minutes, 3-4 minutes, just to fix these ideas: restriction, partition of unity, extension, degrees of freedom, and so on in a few different configurations, right? So it's very, very basic, but just to make sure you understood all this. Huh? So let's start. Again, you have an overlapping mesh. You have a mesh of the domain, right? You want to solve AU equal F and so on, restriction operator and so on. So as I explained, the restriction matrices are just Boolean matrices corresponding to the restriction operators here, right? So this is how the Boolean matrix looks like. So how does it work? So if you apply it to a global, vector, it will just select a few entries corresponding to the local domain. So restriction operator, prolongation operator, you have local Dirichlet matrices. So you have A, it's a global Dirichlet global matrix. If you want to get a local matrix, you apply this restriction, extension operator, a restriction operator to the matrix, then extension, right? Partition of unity, I explain. Okay, so now an example. How do I build this object? So let's suppose I have this set of indices or degrees of freedom. So it's very, very basic. So I have 5 of them. I want to have a partition into these 2 sets of degrees of freedom. So I have 1, 2, 3, and 4, 5. So it's very, very, very basic. This is N1, this is N2. Now the restriction and partition of unity matrices. Restriction matrix, it's very easy. It's just a matrix 3 times 5. So 5 from the global number of degrees of freedom. This is the local number of degrees of freedom. And the second restriction matrix is just 2 times 5, right? Partition of unity is just identity in both cases, because why is that? Because here you don't have any overlap between these domains. So now if you apply the usual relation, you'll see that this is verified. Now if you want to have something with overlap, so let's suppose you have again 5 degrees of freedom here, and you want here 1, 2, 3, 4. This will define the first set, 3, 4, 5 the second set. And so that means you have an overlap, and the 3 and 4 are the overlapping degrees of freedom. So again, restriction are pretty straightforward. You just a rectangular matrix, you select the first 4 here and the last 3 here. And now partition of unity, so here you have the freedom. Here I just put 1/2 because it's easier to understand. So you see here I have the overlapping degrees of freedom. You just need to put some weights in such a way that the final relation, the sum of Ri, Di, and Ri transpose will be equal to identity. Obviously, here you can put something else. Okay, so now what happens if you put just exactly 1? Because you could have this situation, right? So again, partition of unity, you just put 1/2 when you have this one. I think you got the idea. So now, how does it work in real life? How you can get the set of indices of the partition of and the partition of global domain in the sense of degrees of freedom. So this is done usually automatically. So suppose that you have a mesh, which is generated by a mesh generator. You can use an automatic graph partitioner like Metis and Scotch. And this will create a connectivity graph for a given matrix. And obviously, 2 indices are connected. The matrix coefficient is non-zero. And even if it's not symmetric, connectivity graph will be symmetrized. And you have an algorithm that will find a good partitioning even of highly unstructured meshes, right? So the idea of this mesh partitioner is that they try to balance the computations. So that means they will create let's say, almost, balanced partitions of the global. And they will try also to minimize the size of the overlapping region. So that means they minimize the communication between different processors. So now let's have a look. What kind of, you have two different kind of partitions. So it depends on if you use, for example, finite differences or finite elements. So these are, two different kind of methods. So let's suppose that you have a finite differences. So that means the degrees of freedom are located here at in the points of the mesh, right? So you have a partition mesh or Metis or Scotch will give you this partition into local degrees of freedom, and in general, Metis and Scotch will give you the non-overlapping partition into degrees of freedom, right? So how do you build your overlapping partition? So in order to build overlapping partition, what you do is you look at the neighbors of each point here and you add layers, overlapping layers and so on. So in this way you create the overlapping domains, right? So keep in mind that you don't have naturally the overlapping domains for free, okay? In general, you need to do some extra work. Okay, so here if I were to give you a, let's say, mathematical formula for the partition of unity, if you look at all these guys here, so what is the partition of unity of the given point here? So this would be roughly, in this case, 1 over the number of domains that contains a given degree of freedom, okay? So if this belongs to 3 domains, it will be one third and so on. Okay, so now if you have finite elements, it's slightly different because the partition won't be done in this manner. The partition, this will be the computational domain. It contains elements instead of just a cloud of points. So if you want to partition now the domain, use Scotch Metis. It will partition along the edges of this mesh. And again, you need to add layers in order to create the overlapping partition. But now you need to consider now the set of degrees of freedom in the sense of the finite element degrees of freedom. Okay, so it's a bit, it's slightly more complicated. Okay, so again, the partition of unity again is the diagonal matrix containing, it's 1 over mu k being the multiplicity, so the number of domains that intersect the support of the given basis function in the finite element sense. And the restriction matrix is considered in the sense of finite elements, so it's just the kind of interpolation matrices between finite element spaces, which are local and global. Okay, so now I want to summarize now everything. So let's look again into this discretized Poisson problem. So I have a decomposition of the degrees of freedom into local degrees of freedom. I have restriction operator, extension operators. I have, these are local solves. So what is happening is that I'm updating in domain J at the iteration n+1 from the previous iteration. Here is the local residual. I restrict local residual. Here I solve locally, and then I update the previous iterate, and I'll get the new iterate. Okay, so this is what one domain will do. I use the partition of unity, and then I assemble everything in order to get the global solution here. And that's it. So I get my first algorithm, domain decomposition algorithm, right? So in fact, this is the discretization of the original Schwarz algorithm, as you have seen it in the very beginning. Now, the thing is that here a lot of subtleties, so probably you can ask me a bit further, and also Martin was among the first people who identified the fact that this was the exact discretization of the original Schwarz algorithm. And this bears the name of RAS, restricted additive Schwarz, right? But the discrete version of this was discovered independently by Kai and Sarkis in 1999, and later on, the link with the original Schwarz was established. Okay. Now I can introduce another notation, right? So as I said, Martin with one of his postdocs or PhD students, so he showed that the discretization of the classical Schwarz algorithm is in fact the algorithm that you have seen here, which is called RAS. Okay, so this algorithm can be written in this way, as I said, with the notation that I introduced at the very beginning. So can be seen as a stationary iteration, like a block Jacobi algorithm in some sense, right? So un plus 1 is equal to un. Applied to this m RAS minus 1, I explain what it is. And this is the residual of the global residual. Okay, so now the question is, what is this m RAS? M minus 1 RAS that appears there. So this m minus 1 RAS that appears there is exactly the expression that I show you here. So it's restriction operator, local solve, partition unit extension, right? So let me go back. This is probably the last things that I will explain in this first part. So if you look closer to this iteration, you see that it's a stationary iteration, but it's a preconditioned stationary iteration. It's something that you have seen in the numeric analysis, third-year numeric analysis classes, right? So it's a stationary, preconditional stationary iteration, where the preconditioner, this is the first time I'm mentioning this, comes directly from the decomposition into subdomains. Okay? So this is the moment I will try to speak about domain decomposition methods as iterative solvers and domain decomposition methods as preconditioner. Okay, so up to now I defined this, and this was my domain decomposition method. So you see it's a preconditioned stationary iteration. So that means I can do better than just a stationary iteration, and I can keep only the preconditioner from this idea, from this formula. So now the question is, I have different ways of writing this preconditioner. So I said that this is my reference method. It's RAS, which corresponds to the discretization of the original Schwarz method, but I can also define variants of this, like additive Schwarz method, where I remove the partition of unity, or just to be democratic, because this one is not symmetric, I just can put partition of unity on the left and right. I can also replace the local solve by something else, and so on. So we have a lot of different variants of this. Yeah, let me see how much. I probably skip this part. I just try to get to the precondition part, right? Right. To summarize, so my original Schwarz method, it's a stationary iteration in which you have a preconditioner for free. So now the idea is that since I have a stationary iteration, this stationary iteration is not at all very fast. So it's not something that you would use generally, a stationary iteration, to solve a linear system. So that means from this, you just keep the preconditioner part, and you use the preconditioner into a Krylov method, which is it's a lot faster. So okay. So that means instead of just using in a stationary iteration, as I said, I take this, I use in the GMRS, CG, or by CG step. And if I do that, everything will be a lot faster. And also, I can keep the best from the domain decomposition method, so I keep the preconditioner part. So now I probably have a few more minutes just to show you some convergence curves. So I just skip this part. Okay, so these are some numerical simulations done with the FreeFEM software. So I just want to solve a diffusion problem. So this is a solution to some diffusion problem with some boundary conditions, right? And I just want to apply the iterative version, so Schwarz iterative algorithm. And here are convergence curves, so that means I plot the residual, the global residual, as a function of the number of iterations, right? And here are convergence curves. So since they are block Jacobi methods, you know, in spirit, that means the curves will be straight lines. You have a linear convergence. And you see that this convergence will depend on how much overlap you put here. So if you increase the overlap, you have a faster and faster convergence. You have here is 2 meshes overlap, 5 and 10 and so on. So you get a faster convergence. But this is the purely iterative method. So now if you want to apply, as I explained you before, the Krylov acceleration, so you can use here a conjugate gradient, and you do exactly the same kind of test. So here you can see the residual depending on the number iteration, and you increase the overlap. So you see that the iteration count is far lower. It's half, roughly half. And it's a bit less sensitive to the overlap here, right? You have a Krylov acceleration to the... Okay. So I think I finished now. I have 45 minutes. So yeah. So I think this is all I wanted to say. It's just to introduce notations and explain the iterative versus Krylov version of the domain decomposition method. So yeah, that's pretty much it. Thank you.